Now that we've talked about even and odd functions, let's go through a few more examples where we actually want to find the Fourier series for a 2π periodic function. I'll note that you could look back at the example we did in an earlier video. We went through this long process. If you look back at that, that was an odd function, and that realization would have saved us time if we could then immediately see that a sub 0 and a sub k would be 0 in that case. So for this example here, one thing I want to recommend really with any example is I would start off by sketching the graph. It can be a little tough to decide if something is even or odd just by looking at the function, especially when it's a piecewise function. So if I were to sketch out this graph, it's telling me that from 0 to pi, I could draw y equals x. And from minus pi to 0, I would instead draw y equals minus x. And it's really enough to simply draw that part for me to see from this that this is actually an even function. And if I were to continue by drawing out more parts of this, this is more of just a recap of the periodic functions. If you had to draw more of this function, once you've drawn a full period like we've done here, what I can do is take that and kind of imagine picking it up and moving it over. So we get this kind of V. If I were to sketch the graph between, say, pi and 3π, it would look just like that. That's what the periodic property has to be. And likewise, we could continue it from minus 3π to minus pi, looking just like that. But either way, I can see that this is symmetric about the y-axis. And so while it's not necessary for me to observe this, this is going to save me a little bit of time. F of x is even. And that means that b sub k is 0 for all k. So we don't even need to try to find those coefficients in the Fourier series. Another plug here for why graphing this is important. Notice that in the piecewise function, it would have been really easy for me to kind of convince myself that this is odd because y equals x is an odd function and y equals minus x is an odd function. But the way these have been pasted together in this piecewise function ends up drawing out an even function. So in general, if you get started with one and you're trying to take advantage of this potential time saver, I would take the little extra time to really just plot the function. So this means I only have to go through the process of finding a sub 0 and a sub k. We can't assume that those are going to be odd. Or excuse me, they're not odd, but we can't assume those are going to be 0. So a sub 0 is 1 over 2π, the integral from minus pi to pi of f of x. Now, another potentially helpful observation is, yes, we know f is not odd, so that's why I couldn't say a sub 0 was 0. But f is even, and one thing we said we could do is write this as twice the integral from 0 to pi. So again, thinking about our properties for even functions. So again, the 2 that I'm putting up here is a reflection of the fact that on this even function, I took the integral over from just 0 to pi rather than minus pi to pi. And what we'll point out is that this often makes it a little bit easier to evaluate the bounds at the end. So again, not a necessary requirement, but it might be something that you find to be helpful. So in this instance, the other thing that's nice is I don't have to split this up into 2 pieces anymore. On the interval from 0 to pi, the function is just defined to be positive x. So canceling the 2 out front with the 2 in the bottom, I get 1 over pi. And we just have to evaluate this. The antiderivative here is going to be x squared over 2. And notice the 0 contributes nothing, but I'm going to get 1 over pi times pi squared divided by 2, which simplifies to pi over 2. So I'm going to remember this for later, because that's going to be part of my Fourier series. Again, if you had gone through this and not taken advantage of the even property with the integral, you should get the same answer. If I now move on to finding my a sub k's, we need to integrate 1 over pi times f cosine kx from minus pi to pi. And we have an even function times an even function, f times cosine. So yet again, that product is even. So not a necessary simplification, but I, yet again, could say that this is twice the integral from 0 to pi of the very same integrand. And again, one nice thing in doing that is that on that interval from 0 to pi, f of x is just equal to x. So I don't need to go through a breaking this up into two pieces. So we are left with 2 over pi, the integral from 0 to pi of x cosine kx. Now notice here that I'm going to need to use integration by parts to evaluate this integral. So I'm going to let u equal x, du equal dx, dv equal cosine kx, and then we can take advantage of the fact that we've already had to think about the antiderivative of cosine kx in our previous example for Fourier series. So we're going to get a 1 over k times sine kx. So again, this is just my scratch work. Using this, I still have the 2 over pi, and now I have x over k sine kx. This is evaluated from 0 to pi. And then we have minus 1 over k, the integral from 0 to pi of sine kx. So this is what we need to evaluate. Now I'm going to pause and address the first part, and by that I mean this part here. And notice that the two things going on. When you plug in the lower bound of 0, sine of 0 is 0. You're also multiplying by x, which is 0, so that's certainly going to evaluate to 0. When we plug in that upper bound of pi, the x over k would be pi over k. However, as we addressed in the last example, sine of k pi is going to always be 0 for these whole numbers k that we're looking at. So I can notice, whoops, I didn't mean to erase anything. I can notice here that my first part here is going to go to 0, and I'm just going to focus on what's left over. So when I do that, the antiderivative of negative sine is going to be cosine. And so we have 2 pi, and we have 1 over k. And then we're going to have another 1 over k sine k, or excuse me, cosine kx in evaluating this integral. And we're evaluating this from x equals 0 to x equals pi. So when we do this, we are going to get, let's see, I'll kind of section this off. We're going to end up with now 2 over pi k squared times cosine of k pi minus cosine of 0. So I want to point out again that as you do more and more of these examples, these will start to become more familiar. Already, I'm recalling how we dealt with a similar kind of situation in our last example. So I know that cosine of k pi is either positive 1 or it's negative 1, and it depends on when k is even or odd. And so I'm likewise going to be able to break this thing up into two cases. One when k is even, and one when k is odd. So when k is even, cosine of k pi is positive 1, which would always mean that this, in parentheses, would simplify to 1 minus 1 or 0. When k is odd, then we would get minus 1 minus 1, so minus 2 in there, and that would result in a coefficient of negative 4 over k squared pi. So remember that what this is our a sub k's. So we have our a sub k coefficients. We earlier found a sub 0 to be pi over 2. And so I go back to my definition of the Fourier series. And the Fourier series here would be the constant a sub 0 plus the sum of the cosine kx terms, with coefficient a sub k. Now, I'm going to use what we observed in our last example to help me put this in sigma notation. If it's helpful, you could still start to write out the terms like we did before to look for the pattern. But what I want to do is represent my coefficient where I have to be a little bit careful with what I put in for the role of k, because we want to only represent odd k values, skipping over the even k's because those have coefficient 0. And we observed last time that the nice way to do that is to replace k with 2k minus 1. And importantly, I'm putting it in both places that k would have played a role here so that those match. I don't need to write the sum from k equals 1 to infinity of b sub k times sine of kx, because, as we said in red up here, we know that the b sub k's would be 0. So at this point, we're done, and our final answer is what we have down here. This is our Fourier series. And I want to go through another example. Just like I said, the more practice, the better. So this video will probably be a little long because this is not quick to find a Fourier series. But here, let's do the same thing. So we're going to have the task of find the Fourier series for the 2 pi periodic function f of x such that we know that our f of x is defined to be minus x when x is between negative pi and 0, and 0 when x is between 0 and pi. So like before, my natural inclination is to start by just sketching the graph, just even over a full period. So here, like before, we get y equals negative x when we graph this from minus pi to 0. But from 0 to pi, we get just y equals 0. So note that f of x is neither even nor odd. And that just means that there aren't any shortcuts here. So we have to find all coefficients. I don't get to assume any of them are 0. And I also wanted to point out that just by doing this example, that it is really helpful when you notice that you have an even or odd function, but that's not always going to be the case. Many times you're going to encounter functions that aren't even or odd, and we can't really use any of those simplifications. So now I want to go through and find my sets of coefficients. A sub 0 is 1 over 2 pi, integral from minus pi to pi of f of x. So here we do have a piecewise defined function, but one of our pieces defines f of x to be 0. So I could break this up into 2 pieces where I'm adding the integral from minus pi to 0 of f plus the integral from 0 to pi of 0. But the integral of 0 is 0, so we can always here write this as just the integral from minus pi to 0 where f of x is defined to be negative x. So again, I am not rewriting this interval because of any even or odd property. Maybe just for this first one, I'll point out that technically what's happening is you're integrating from 0 to pi 0, and I'm just leaving that off. So I could really just jump straight to what I have here. So for your work, you would not need to demonstrate why you left off that integral I'm writing second there. Okay, so focusing on the integral that we do have here, my antiderivative, I'd get here a minus x squared over 2, and we're evaluating this from minus pi up to 0. So just have to be careful. We have several minus signs going on there. So I would plug in 0 minus what I get when I plug in minus pi. And when I do that, I will get negative minus pi squared over 2. And these minuses become a plus, and then of course I'm squaring the negative pi. So this all is positive. So we will get pi squared over 8 pi. And whoops, sorry, this should, I already pulled my 1/2 out. So this should be 4 pi. And then we can cancel a factor of pi. And this should be now pi over 4. That is our constant term, our additive constant. So let's move on to a sub k, where we want to find 1 over pi, the integral from minus pi to pi of f times cosine of kx. For the very same reason we observed that this went to 0 up here, 0 times cosine of kx would integrate to 0. So I only need consider the integral from minus pi to 0, where I can replace f of x with negative x. So just like above, I can use integration by parts to evaluate this. So I would let u equal my minus x and dv my cosine kx. So that's going to allow me to rewrite this now as 1 over pi, and we have negative x over k sine kx. We're evaluating that from minus pi to 0. And then minus a negative, so plus 1 over k integral from minus pi to 0 of sine kx. Now, just like we observed in the previous example, I have the sine of kx where I'm evaluating that either at x equals 0 or x equals minus pi. That's going to always evaluate to 0. So I can reduce this, and now I'm left with, whoops, 1 over pi. So let's say 1 over k pi, taking that one out back. The antiderivative of sine of kx is now going to be negative 1 over k cosine kx. And we're evaluating this from x equals minus pi to 0. So we are left with negative 1 over k squared pi. And we have cosine of 0 minus cosine of minus k pi. Now, you could call that cosine of k pi because that's even, but what I'll point out is that that's either plus 1 or it's minus 1, just for the very same reason that we said that about cosine of k pi. So I know now that I can write this as a piecewise defined function where I want to distinguish between what happens when k is even and what happens when k is odd. So when k is even, we happen to yet again get that cosine of 0 equals cosine of minus k pi, so the difference is 0. And when k is odd, the parentheses would give me 1 minus a negative 1, so 2, and multiplying that by what's out front, we would get minus 2 over k squared pi. So you will encounter some examples where you don't get 0 for when k is even. In hindsight, I'm realizing all of my examples show this. And yeah, I think in fact, we will witness that for b sub k. But at this point, I just want to keep tabs on the fact that this is my a sub k. And so we're almost done. We need to find b sub k, which would involve 1 over pi, the integral from minus pi to pi of f of x times sine kx. And again, that can be written as just looking at the interval from minus pi to 0, because on the other part of this, f of x is defined to be 0. So we'll use integration by parts again, letting u equal minus x, du equaling minus dx, dv equaling sine kx. And in this instance, the antiderivative would be minus 1 over k cosine kx. So we would get 1 over pi. When we multiply u times v, that becomes positive x over k cosine kx. And then we get minus, again, the product of v du is positive, so it still is minus 1 over k, the integral from minus pi to 0 of cosine kx. And I should have put my evaluation bars here. So unlike the last example, I'm noticing that I'm not going to be able to just wipe out cosine kx when I evaluate at 0 and minus pi. So I'm going to hold off on that part and just evaluate that second integral. So I'm going to have 1 over pi. We have x over k cosine kx. And then when we anti-differentiate the minus 1 over k cosine kx, that's going to bring out another 1 over k. And it will be 1 over k squared sine kx. And we're evaluating this whole thing from minus pi to 0. So in this example, it's the second factor that will always evaluate to 0 when we plug in 0 or minus pi. And let's look at what we have left. I'm left with 1 over k pi. When we plug in our bounds, we'll have 0 times cosine of 0 minus negative pi times cosine of minus k pi. So this really only reduces to that one term because we can get rid of 0 times 1. And we're left with positive pi over k pi cosine minus k pi. The pi's cancel. And again, I'm recognizing that this cosine is plus or minus 1. So this is going to, first of all, be a situation where this is not going to be 0 when k is even, but instead, this tells me that my b sub k can be expressed in piecewise form. When k is even, cosine of minus k pi is positive 1, so this coefficient would be positive 1 over k. And when k is odd, cosine of minus k pi is negative 1. This coefficient would be negative 1 over k. So here I found all of my coefficients, and I just want to put them back into the formula. So the Fourier series here is, first of all, we go back and grab our a sub 0, and we found that to be pi over 4. Then we look at our sum of the cosine terms, whose coefficients were the a sub k's. We want to represent that so that we only have odd k's represented. So this negative 2 over k squared pi will become negative 2 over 2k minus 1 quantity squared pi. And we will likewise replace the k inside of cosine with 2k minus 1. That is from experience from the previous examples. And then finally, we have to include the sum of the sine terms, and our coefficients of those are exactly what I have at the top of the page here. And I don't need to rewrite that in a way to skip over any k values. Instead, the way I could concisely write that pattern is to represent the numerator as either positive 1 or negative 1. And we've seen that we can do that by writing either negative 1 to the k or negative 1 to the k plus 1. So I'll point out here the way to decide is I want this to be negative when k is odd, and we can accomplish that if I just write it as negative 1 to the k. If the negative sign were when k was even, then I would replace that with either k plus 1 in the exponent or k minus 1. And then again here, because we're not skipping over any k's, likewise I put that same k value in there. So it's a long process, but after going through this entire thing, we get here that this is going to be our final answer for the Fourier series of that 2 pi periodic function that we were looking at.